Hi all. Good evening, everyone. Okay, so let's start now. Today we will study a new type of graph, a very special type of graph, that is trees, and also another is rooted tree. So these two concepts we will study today. Let's start with first. Let's see some questions on complete bipartite graph. We have already seen what is complete bipartite graph. That is your a bipartite graph in which every vertex of part A is adjacent to every vertex of part B. For example, this is your K26 because these are the two vertices in part A, these are the six vertices in part B, and you can notice every vertex of part A is adjacent to every vertex of part B. Okay, so finally I can say that this is your so this is the concept of complete bipartite graph. Now the question is maximum number of edges in a bipartite graph on n vertices. What do you think? What is the answer? For example, if I ask you what is the maximum number of edges possible in a bipartite graph on 4 vertices, then what that will be? This is edges. Okay, don't worry, this is just a this is just a representation, but you can remove it. Actually, why this e? Because see, graph is set of vertices and set of edges, right? Graph is set of vertices, set of edges. Now a bipartite graph, in a bipartite graph, this v is basically a union b. You have two parts of in bipartite graph. So that is the reason I can say that in bipartite graph what will happen. Remember, you know that in bipartite graph, you know that we partition the vertex set. This we partition into two partitions. Okay, so the bipartite graph we can write like this: G A comma B E. Is this clear, Alok? Normally the graph is set of vertices, set of edges. This is the normal graph. But a bipartite graph, in a bipartite graph, the vertex set we partition into two parts. There are two parts. For example, this is a part, this is a part. Okay. For example, this is a part, this is a part. So I can say in a bipartite graph, we have two parts. So we can write like this. Okay. Anyway, this is just a notation. You don't have to worry about. Tell me, maximum number of edges possible in a bipartite graph on 4 vertices. Tell me one thing. What is unknown here? What information is unknown? In this question, what information is unknown? We want maximum number of edges. This is what we want. But what information is unknown? Cardinality of both sides. Very good. This is unknown. Like, what is the cardinality of two parts? Because this is your number of vertices. So I can say number of vertices is 4. But we don't know. Okay, what we do, because this is a bipartite graph. So what we do, this vertex set we divide into two parts. This vertex set, what we do, we divide into two parts, A comma B. Now we don't know. For example, if I give you particular A comma B, if I give you particular A comma B, for example, if I give you one vertex here and 3 vertices here, then tell me what is the maximum number of edges you will get. What will be the maximum number of edges? If one vertex here and 3 vertices here, then the maximum number of edges will be 3. So I can say maximum number of edges, that will be 3 if I do this. But from this question, we don't know what is the cardinality of two parts. We don't know. Okay, so for example, if I do this like 1 comma 2 I put here and 3 comma 4 I put here, then what will be the maximum number of edges? Now the maximum number of edges will be 4. Now the maximum number of edges will be 4. So this is the idea. This is the idea of this question. So in this question, what will be the answer? The question is asking, you have a bipartite graph on 4 vertices, then what is the maximum number of edges? So the final answer, what that will be? The final answer, that will be 4. Because whatever you do, only this you can create. Only this you can create. Like this 4 is the maximum. You cannot create more than this. Is this question clear? I just want you to understand the question. Is the question clear? Maximum number of edges in a bipartite graph on 5 vertices. Let's see this question. Let's see on 5 vertices. Now what this question is asking, You have a bipartite graph on 5 vertices. So remember your graph is bipartite graph on 4 vertices. So this is your vertex, this is your set of vertices. Here you have two part A comma B, and this is your set of edges. This is a bipartite graph. Okay, now in this question, Avni, the question is asking maximum number of edges. This is the question asking. Now which information is unknown? Which information is unknown? The information that is unknown is what is the cardinality of A comma B. This information is unknown. For example, if I ask you this question, that you have a bipartite graph. If I ask you this question, you have a bipartite graph. Okay, and there are, let's assume, 7 vertices. 7 vertices, 3 in part A, 3 in one part, and okay, 4 in part B. 4 in part B. Or maybe I can say maybe 5 in part A and 2 in part B. If I give you this question, so you have a bipartite graph. Your graph is a bipartite graph in which you have two parts, A comma B. These are the two parts, and these are the set of edges. And what I'm saying, this is your vertex set. Now tell me, now what is the maximum number of edges? For this question, what will be the maximum number of edges? Tell me for this question. Now in this question, this information we have total 7 vertices, 5 in part A, 2 in part B. So in this part you have total 5 vertices. Okay, and in this part you have total 2 vertices. This is your part A, this is your part B. For this question, what will be the maximum number of edges for this question? Now for this question, answer will be 5 into 2, 10. Because we want maximum number of edges. This is what we want, maximum number of edges. So what you can do, you can create a complete bipartite graph on 5, 2. This you can create. You can create a complete bipartite graph. This is what you can do. Like this you can do. Correct? So you can create this complete bipartite graph and the answer will be 10. Is this clear? Because here we know how many vertices we have in part A, how many vertices we have in part B. This information we know. Part A has 5 vertices, part B has 2 vertices. So maximum number of edges. How to get maximum number of edges? How to get? Tell me how to get maximum number of edges? Create a complete bipartite graph. To get maximum number of edges, if you want to get maximum number of edges, then create complete bipartite graph. Then create complete bipartite graph if you want to get maximum number of edges. So this is the idea. Okay. Yes, minimum number of edges is 0. Of course, Saurabh, minimum number of edges is 0. So anyway, so if you want to get maximum number of edges, then you can create complete bipartite graph. Now, in this question, which information we don't have? In this question, we know that total number of vertices is 5. In this question, we know total number of vertices is 5. But we don't know how many vertices are in part A, how many vertices are in part B. For example, the part A, okay, we don't know which will give us, like, we don't know which situation will give us maximum number of edges. We don't know which situation will give us maximum number of edges. For example, will this situation give us maximum number of edges? Okay, will this situation give maximum number of edges? Like, which situation will give maximum number of edges? Which situation is going to give maximum number of edges? So you can notice here, what is the maximum number of edges? Tell me here, what is the maximum number of edges? That will be 4. Here the maximum number of edges that you will get is 4. Here the maximum number of edges that you will get is that will be 6. That will be 6. Here the maximum number of edges that you will get will be 6. Okay, and here the maximum number of edges that you will get is 0. Correct? So this is the idea. Okay, is this clear? Is it clear to everyone? So finally, for this question, what will be the answer? Finally, for the final answer, what is the final answer? Because we want maximum number of edges when you have 5 vertices. So this situation will give us maximum number of edges, this situation. So the maximum number of edges you can get is 6. This is what I'm saying. You have 5 vertices, and with 5 vertices in a bipartite graph, you can get maximum number of edges 6. You cannot get more than 6. This is the maximum number of edges you can get. Is this question clear? What this question is asking, is that clear to everyone? Let me know. Now let's solve this question. So we want maximum number of edges. This is what we want in a bipartite graph on n vertices. So your graph is bipartite. In your graph, this is your vertex set, and these are the two parts a comma b, and you have edges, and the cardinality of vertex set is given to you as n. This is given to you. Then what is the maximum number of edges we can get? What that will be? Okay, so here what we can do, see, we don't know which situation will give us maximum number of edges. We don't know. So what we have to do, you know that if you have a, if you have b, if you have a, you have b, then what is the maximum number of edges? Please tell me. Then what is the maximum number of edges? If you have a, you have b, then that will be number of vertices in a multiplied by number of vertices in b. Yes or no? Yes or no? This will be the maximum number of edges if a is this, b is this. We don't know how many vertices are in a, how many vertices are in b. So what we want to maximize, this is what we want to maximize. We want to maximize, okay, cardinality of a multiplied by cardinality of b. This is what we want to maximize. This parameter we want to maximize, correct? This parameter we want to maximize. Let us assume that a has, let us assume that a has m vertices. Let us assume, then what will be the number of vertices in b? Then what will be the number of vertices in b? That will be n minus m. So what we want to maximize, we want to maximize this value. This value we want to maximize. Is this clear? I am going very slowly, step by step. I am going step by step. This parameter we want to maximize. We don't know how many vertices are there in a. We don't know how many vertices are there in b. But we want to maximize. We know, okay, that the maximum number of edges will be this. Okay. Now finally, what we want to maximize, we want to maximize this value. Our target is to maximize. This is what we maximize. We want to maximize. What is variable here? In this value, which is variable? This is called, this is fixed. This is fixed. This m is a variable. This m is a variable. Okay. This n is fixed. So we want to maximize. Then what we do? See, you will study in calculus. In calculus subject, you will study this. In calculus, you will study. Don't worry about it. In calculus, you will study. There is something called maxima minima. This maxima minima concept you will study in calculus. Okay. So if you don't understand this, what I'm going to do, if you don't understand, don't worry about it. In calculus, you will study maxima minima. After that, this question is very easy, extremely easy, this question. Okay. So anyway, what we will do, so this is the parameter we want to maximize. This f equal to m into n minus m, and this is what we want to maximize. Now to maximize this, then what we do? Then we do df dm, because this m is the variable. This m is the variable. Array n is fixed. This n is fixed. M is variable, Saurabh. M is variable, right? How many vertices you put here, that is variable. How many vertices you will put here, that is variable. That is not known. We don't know that. Okay. So finally, what we will do? We will do this. We will do differentiation with respect to the variable. We will do differentiation with respect to the variable. So what I will get? So this is basically d dm mn minus m square, and that will give me n minus 2m. That will give me n minus 2m. Okay, so this is what we will do. Basically, we will do the differentiation. This differentiation we will do to maximize. Remember, to maximize, we do the differentiation. This you will study in the maxima minima. So don't worry about it if you don't understand. Okay, just chill, don't worry. So this differentiation you do, you will get this value. Now, what we do, the second thing, what we do, we put this equal to 0. We put this equal to 0. We put this equal to 0. So from here, m is equal to n by 2. So from what we will get m equal to n by 2. So this will this value, so this value will maximize. So if you want to maximize, then this value will maximize. So remember, finally this is the point. If you want to get maximum number of edges, so this is the final point, that m should be equal to n by 2. What it means? It means here you should have n by 2 elements, and here also you should have n by 2 elements. Okay, very simple. Both sides you must have n by 2 elements, means their cardinality must be same if you want to maximize. So this is the final conclusion. What is the conclusion? You have a bipartite graph. You have a bipartite graph. Remember, your graph is bipartite. Okay, so your graph is bipartite. G, A, comma B, these are the partition. These are the partition, and this is the number of edges. Okay, now so so these are the, just wait, please wait. Array, what you will do if your n is odd? If n is odd, then what you will do? Then it is very simple. Just put, for example, if n is 7, then what you do? The simple n by 2 element you put here, n by 2 element you put here. Just put n by 2 here. So what you do? Here you can put 3, here you can put 4. So on one side you put n by 2 floor, on one side you put n by 2 seal. So if your n is odd, then what you do? You put on one side you put n by 2 floor, on another side you put n by 2 seal, because total number of vertices should be n. So this is easy. For example, if you have 7 vertices, then you can put half vertices here, half vertices here. Is this clear? If your n is odd, then you can put half of them here, half of them here. So on one side you can put this floor, on other side you can put seal. Okay, clear? So this is the conclusion. If your graph is bipartite, in which you have 2 parts, this is the vertex set and you have 2 parts, and this is given that vertex set has number of elements. So these are the number of vertices. Then how to get maximum number of edges? Then to get maximum number of edges in bipartite graph, to get maximum number of edges, then what we will do? To get maximum number of edges, what we will do? We will basically, this is what we will do. We will put half elements here, and we will put the remaining elements here. We will put half elements here, and we will put remaining elements here. Okay, this is what we will do to get to get maximum number of edges. So what will be the maximum number of edges? That will be this multiplied by this. Correct? This will be your maximum number of edges. N by 2, basically half. Okay, what you can do, if you have 7 vertices, you can put 3 here, 4 here. This is what you can do. So just put half. Okay, just put half. This will give you maximum number of edges, and this will be the maximum number of edges in a bipartite graph on n vertices. If your bipartite graph has n vertices, then this is the maximum number of edges you can create. Is it clear to everyone? Tell me, is this clear? Any doubt, anyone? Very simple question. Let me know. Okay, so let's see now. So remember, if you have n vertices bipartite graph, if you have n vertices bipartite graph, then what is the maximum number of edges you can get? N vertices bipartite graph can have maximum number of edges. What? N vertices bipartite graph can have maximum these many edges, like n by 2 whole square, these many edges, n by 2 whole square edges. Let's assume n is even. Okay, let's assume n is even. Okay, so n is even. You can just assume that n is even. Okay, anyway, what I'm saying that, so if you have approximately, this is the maximum number of edges. Okay, now, so tell me, if you have n vertices bipartite graph, then maximum these many edges you can have. This is the maximum number of edges you can have, n by 2 whole square, or I can say that n by 2 floor, n by 2 seal multiplication. This is the exact value. This value is the exact value. Okay, now, so Tell me one more thing. If a graph has more than these edges, if a graph has more than these edges, then what you can say? If a graph on n vertices, if a graph on n vertices has more than n by 2 whole square edges, then it cannot be bipartite. Then it cannot be bipartite. So this is very simple. It cannot be bipartite. Yes or no? Or it will not be bipartite. Sandeep, yes or no? So if your graph, if you have a graph, if you have a bipartite graph on n vertices, then maximum these many edges can be there. Maximum these many edges can be there. Let's assume n is even. Let's assume n is even. Okay, then maximum these many edges can be there. If your graph has more than these edges, it means it cannot be bipartite. Okay, so this is the simple point. So remember, n vertex graph with more than these edges is not bipartite. This we have proven. Okay, so very simple. And this we have already seen in the last class. K regular bipartite graph. This also we have seen. See, G is bipartite if and only if all its component bipartite. Yes or no? G is bipartite. So can I say if G is bipartite, for example, is this graph bipartite? Let me give you a graph. Is this graph bipartite? Tell me. This graph. Look at this graph. In this graph, you have odd cycles. So this is not bipartite. This is not bipartite because you have odd length cycle. So this graph is actually not bipartite. A, B, C, D, E. So if you try to, for example, let's try to create a bipartition. So if I put D here, I will put E here. If I put A here, then B is, now there is nowhere to put C. So where to put C? So I can say this is not bipartite. We cannot put C. So this graph is not bipartite. Yes or no? And what about this graph? If I give you this graph, A, B, C, D, E, F, G, H. Is this graph bipartite? Tell me. In this graph is bipartite. Why? Because there is no odd length cycle. There is no odd length cycle. We don't have any odd length cycle. So this graph is actually bipartite. So what will be the partition? What will be the partition? Partition will be like this. If I put A here, then B will go here, C will go here, D will go here. If I put E here, then F will go here. If I put G, then I can put H. For example, I can put G, H here. I can put G here, H here. Okay. So this bipartition will work. Yes or no? This bipartition will work. This partition will work. Correct? So this is what I'm saying. A graph is bipartite if and only if each component is bipartite. Okay, means a graph is bipartite means what? Means does not have any odd cycle. If and only if no odd cycle, no odd cycle, no odd length cycle. So each component also should not have odd length cycle. Okay. No, we need only at least one partition. Sandeep, we only want at least one partition. We only, for example, if I give you this graph A, B, C, then this graph G, this is bipartite. This graph G is bipartite, and this partition will also work. See, this partition will also work. This partition will work. This partition will also work. This partition will also work. Okay, all these partitions will work. So bipartite means you can create a partition. You can create a bipartition. So is this clear? So G is bipartite if and only if no odd cycle. So basically every component also should be bipartite. G is bipartite if and only if every component. Here this component is not bipartite. Here every component is bipartite. This component bipartite. This component is bipartite. This component is bipartite, and this component is also bipartite. So G is bipartite if and only if every component is bipartite. Okay. So these concepts, are they clear? Like maximum number of edges in bipartite graph. How to find that? Maximum number of edges in a bipartite graph. And if you have a graph in which you have more than n by 2 whole square edges, then that graph is not bipartite. So this statement they can ask, if you have a graph in which n vertices graph with more than these edges, then it is not a bipartite. Okay, so that's the idea. Now let's see the next, that is hypercube graph. Are they bipartite? Let's see all of them. Which of them is bipartite? Tell me all the categories which is bipartite. Which graph are bipartite? For example, the first, can I say Kn is bipartite? The second, Pn, path graph. The third, Cn. The fourth, Wn. Okay, the fifth, En. And the sixth, Qn. Which of these graph is bipartite? The 7, Km, N. Okay, so tell me which graph is bipartite. So you can notice there is no odd cycle. So this is bipartite. There is no odd length cycle. There is no odd length cycle in a path. In a path, there is no odd length cycle. So basically, which graph is bipartite? Just see which have odd length cycle. If and only if no odd cycles, no odd length cycles. Okay, this complete bipartite, this is bipartite. Okay, only for, this is bipartite only for n equal to 1, 2. This is bipartite only for 1, 2, n equal to 1, 2. This, else this is not bipartite. Bipartite only for n equal to 1, 2. What about this? This is also not bipartite only if n is even. Only if n is even. Next, what about Wn? What about Wn? What do you think? What about Wn? This is not, because in Wn what happens? Just see what happens in Wn. In Wn you have this vertex, and because of this vertex a triangle will create. Yes or no? In Wn this type of situation will happen. So you are getting an odd length cycle. In Wn, if you notice this Wn, then in Wn you will get an odd length cycle. You will definitely get an odd length cycle. Whatever Wn you take, in every Wn, for example, in every Wn, what will happen? This middle vertex will create an odd length cycle. So very simple. So because you are getting an odd length cycle, so this is, you are getting an odd length cycle. So Wn is not bipartite. What about En? This is bipartite. What about Q? This is your complete bipartite graph. So this is also, and this hypercube is also bipartite. This hypercube graph is also bipartite. Why? What is the reason? Let us see. This Qn. What is this Qn? This is your hypercube graph on how many vertices? Hypercube graph on how many vertices? This is hypercube graph on 2 power n vertices. Okay, so this is the idea. Now, this hypercube graph on 2 power n vertices, this is actually bipartite. This is actually bipartite. You can create a bipartition. How to create a bipartition? Let me tell you. Very simple. What you can do, if you want to create a bipartition, what you can do? You can use the parity. The concept of parity you can use. What you can use? For example, what is parity of a string? What is parity of a bit string? What is parity of a bit string? That is number of ones. That is number of ones in it. That is number of ones in it. Okay. So very simple. What is parity? Parity of a bit string. If I give you a bit string, for example, if I give you this bit string, then what is the parity of this bit string? What is the parity of this? That is 3. Or I can say actually that is odd. Parity is odd or even. Parity is odd or even. I can say basically parity is odd or even. Remember, parity is odd or even. This parity is odd or even, and that is basically defined by that is based on number of ones in it. Okay, so that will be odd or even. So this string has parity odd. What is the parity of this string? This string has parity even. What is the parity of this string? Number of ones is even. What is the parity of this string? Number of ones is odd. What is the parity of this string? Number of ones is even. What is the parity of this string? Number of ones is odd. So parity is odd or even. Is this clear? Parity is basically odd or even. Very simple. Either it will be odd or it will be even. Now what you can do, if you want to create a bipartition of this Q and hypercube graph, then what you can do, this is very simple. You can put odd parity strings here, you can put odd parity strings here, and you can put even parity strings here. Tell me, can you have age between two odd parity string in hypercube graph? In hypercube graph, can you have age between two odd parity strings? Can you have that between two odd parity strings? Just think about it. If I give you, like, okay, if I give you some string, then this will be adjacent to whom? This will be adjacent to whom? Just tell me. This will be adjacent to odd parity only. Whatever you do, you will get odd parity. See, this will be adjacent to, you can notice whatever bit you change, this will be adjacent to only odd parity strings. This will be adjacent to only a odd parity string. Because if I change this, then I will get odd parity. If I change this, I will get odd parity. If I change this, odd parity. If I change this, odd parity. So whatever I change, this will be adjacent to only odd parity string. So I can say that if you have even parity string, then they can never be adjacent. Yes or no? Even parity string, they are not adjacent. They are not adjacent, I can say. Yes or no? Not adjacent. Similarly, odd parity string, they cannot be adjacent. For example, if I put 0, 0 here, like I am putting odd parity means 0, 1, 1, 0, and even parity means this. So now you can notice this is adjacent to this, this is adjacent to this, and this is adjacent to this, this is adjacent to this. Is this clear to everyone? This concept, is this clear? That hypercube graph is actually, for example, this Q3. Look at this Q3. This Q3 is also bipartite. Okay, for this Q3, what you can do? You can put odd parity strings here, or you can put even parity strings here. So, for example, even parity strings, you can put this even parity string here. You can put this even parity string here. You can put this even parity string here and this here. And here you can put odd parity strings like, okay, 1, 0, 0, 0, 1, 0, 0, 0, 1. Now you can notice that they are non-adjacent. Yes or no? They are not adjacent, correct? They are not adjacent. You can notice. None. Are they adjacent? For example, these two, are they adjacent? Tell me. In Q3, in hypercube graph on n vertices, they are not adjacent because they are changing in two positions. The Hamming distance is 2. They are changing in two positions. These two are not adjacent. These two are not adjacent. They are also changing in two positions. Okay, they differ in two positions. So finally, what I can say, like this, I can say this is adjacent to whom? This is adjacent to this. This is adjacent to this, and this is adjacent to this. Correct? Similarly, this string is adjacent to this. This string 1, 0, 0. Okay, so this is adjacent to this one, and this is adjacent to this one. Yes or no? Like this you can do. Similarly, this string will be adjacent to this one. This string will be adjacent to this one and this one. Okay, so like this you can do. And last, this 0, 0, 1. This 0, 0, 1. Where, okay, this 0, 0, 1. This will be adjacent to 0, 0, 0. This will be adjacent to 0, 1, 1, and this will be adjacent to 1, 0, 1. So this is the idea. Okay, I hope this is clear. So what we can do, remember, hypercube graphs are bipartite, and what we are doing in hypercube graph, what we are doing. So why they are bipartite? Because what you can do, all the odd parity strings you can put in one part, and all the even parity strings you can put in another part, whatever hypercube graph you take. So this is the idea. I hope this is clear. So remember Qn for all n is bipartite, is bipartite, is bipartite. And the partition, this Qn actually I can write like this, G, where this will be the partition. Odd parity strings, you can put odd parity strings in one part, you can put even parity strings in another part. Okay, and these will be the edges. So I can say this whole thing, this is the partition of vertex set. This is part A, this is part B. Part A, part B, you have. Okay, so this will be your part A. Okay, and this will be your part B. So you have two part A, part B. And you can notice that this is the bipartition of a Qn. Okay. This Qn, can I say this is complete bipartite graph Qn? Can I say this is complete bipartite graph? Can I say this is complete bipartite graph? No. Complete bipartite graph, the answer is no. You can notice this Q3, you can notice this is not complete bipartite graph. This is not complete bipartite graph. Yes or no? Correct? Next. What, this is your GATE exam question. What will be the answer? Maximum number of edges in bipartite graph on 12 vertices, that will be 36. Because if this is your n, then the maximum number of edges, the answer will be n by 2 floor multiplied by n by 2 seal. This will be the answer. This will be the maximum number of edges in bipartite graph. On n vertices. So very simple question. Okay, so if you want to get this 36, then what you have to do? You have to put these 6 vertices here. You have to put 6 vertices here, and you have to put 6 vertices here. You will get an answer. Okay, next, let me tell you one more thing. Okay, in actually, see, whenever they ask you to find maximum, this is a normal. Remember, this is a normal. Like normally this happens. Normally, in graph theory, normally in graph theory or some other subjects, whenever they ask you maximum, minimum, normally in graph theory or in some other subjects, whenever they ask you maximum, minimum, where these are found, maximum comma minimum are generally found where? Are generally found at the corner cases. Are generally found, remember, they are generally found either at the corner cases, either at extreme corner, extreme, I can say, like I can say, extreme, I can say, what I'm saying, extreme partial distribution or symmetric distribution. Either extreme partial distribution, either extreme partial distribution or extreme fair distribution, extreme fair distribution. So what I'm saying, either extreme unfair distribution or either extreme fair distribution. Either you do extreme unfair distribution or you do extreme fair distribution. Okay, this is the simple thing. Like this will happen. This will happen. You can check it out. Okay, like in mathematics also many times this will happen. I am not saying this will always happen. This will not always happen. In mathematics, when we study calculus, when you study engineering mathematics, there many questions you will get where this will not happen. But in all other subjects like operating system, dbms, graph theory, algorithm, or whatever the subjects, like I can say non-mathematical subject, like okay, in engineering mathematics, in calculus, this will not true. This will not be true. Okay, because there we study many questions. You will solve 100 questions. In 100 questions, for almost 50-60 questions, this will be true. If you solve 100 questions, then almost 50-60 questions, this will be true. But in graph theory, in operating system, dbms, in TOC, theory of computation. There, if you solve these questions, maximum minimum questions, if you solve, then mostly this will happen. Mostly this will happen. Okay, like either you do extreme unfair distribution or you do extreme fair distribution. So for example, for bipartite graph, which is working, which is giving maximum, for bipartite graph, which is giving maximum number of edges, the maximum number of edges which is giving number of edges. So if you want to find maximum number of edges, then you can check these possibilities. Either you can check extreme unfair, like all n vertices here, this is empty, and this is all n vertices, like all the n vertices are here. This is extreme unfair, yes or no? And you can also check these, like n minus 1 vertices we are putting here. You can also check this. You can also check this, or you can check n by 2, n by 2, or you can check n by 2, n by 2. So these things you have to check. Are you getting my point? So whatever question they give you, these cases you need to check. This is extreme unfair. This is extreme unfair. This also you can check, where one vertex on one side and the remaining vertices. And this is fair. This is very fair. Okay. So this is the idea. So you can notice this unfair, this will give you minimum number of edges. For this particular question, this will give you minimum number of edges. Yes or no? For this particular question, this unfair distribution will give you minimum number of edges, that is 0. And this fair distribution will give you maximum number of edges, that is n by 2 whole square. Okay. Is this point clear? So this is I can say this is a guideline. Okay, this is guideline mostly. I can say this is mostly this will happen. Okay, either you do fair distribution or you do unfair distribution. So on corner cases you have to check. You don't have to check. For example, if I give you 8 vertices, if I give you 8 vertices bipartite graph, then if I give you this 8 vertices bipartite graph, then you only have to check these, only have to check to get maximum number of edges. And our question is to get maximum number of edges. So what you have to do? What you have to check? Please tell me what you have to check. Actually, now you know the answer, but if you don't know the answer, now you know the answer. The answer you know. The answer is 4 whole square. But if you don't know the answer, then what are the cases you need to check? These extreme cases you need to check, like all the 8 vertices here. Like these cases you have to check, like all the 8 vertices here, 0 vertex here. Or you can check this case, where 1 vertex here, 7 vertices here. Or you can check this case, where 4 vertices, 4 vertices. So only these cases you have to check. On these corner cases, I can say these are the corner cases. These are the extreme, like unfair or fair cases, corner cases. So in these corner cases you have to check. You don't have to check like this, like, okay, you don't have to check like this. For example, 3 here, 5 here. You don't have to check like that. Okay, now let's move on. Now the next topic is cyclic acyclic graph. What is a cyclic graph? The name itself is telling you. Cyclic means there is a cycle. There should be cyclic. Remember, there is a difference between cyclic and acyclic. Sorry, cyclic and cycle graph. What is a cyclic graph and what is a cycle graph? Cycle graph means a cycle. For example, this is a cycle graph and this is not a cycle graph. This is not a cycle graph. But what is cyclic graph? Cyclic graph, this is also cyclic graph. This is also cyclic graph. So cyclic graph means a graph which contains cycle. This type of cycle should be there. This type of cycle should be there. So cyclic graph means it contains cycle. It contains at least one cycle. At least one cycle it contains. And cycle graph you already know. That is this is your C3, C4. Okay, so like this is your C4 and so on. So these are the cycle graphs. For example, this is your cycle graph. But this is not cycle graph. Is this clear? What is a cyclic graph? So cyclic graph, that means a graph which contains at least one cycle. At least one cycle. For example, this graph contains a cycle. So this is cyclic graph, a graph with at least one cycle, at least one. This graph does not have any cycle. Yes or no? In this graph, we don't have any cycle. There is no cycle in this graph. So this is not, this is acyclic. This is acyclic. Now let me tell you which observation you can make. Tell me why there is no cycle here. Please tell me why there is no cycle here. Like, how can you say there is no cycle here? How can you say there is no cycle here? Because if I start at E, can I come back to E by some trail without repeating edges? Can I come back to E? If I start at some vertex, can I come back to this vertex without repeating edges? Tell me. If I start at some vertex in this graph, if I start at some vertex, then can I come back to that vertex without repeating edges? I cannot come, right? But in this graph, tell me where should I start such that I can come back without repeating edges? Tell me where should I start? Where should I start so that I can come back without repeating edges? I can start here. Without repeating edges, I can come back. If I start here, then can I come back without repeating edges? If I start here, can I come back without repeating edges? No. So I can say this is not a part of cycle. This vertex is not a part of cycle. These vertices are the part of the cycle. Because if I start here, then I can come back here without repeating edges. If I start here, I can come back here without repeating edges. So this is the idea. So what is the definition of cycle? A cycle in a graph occurs when some so this is, you can notice, a cycle occurs when some number of vertices are connected to one another in a closed chain of edges. That is your cycle in a graph. A graph that contains at least one cycle is cyclic graph. So this is the definition of cyclic graph. See this. So graph containing at least one cycle, that is your cyclic graph. I can say that there is some vertex. There is some vertex where we can start, follow a trail without repeating the edges, and we can come back. Okay. So this is the definition of cycle. Another definition of cycle, what is that? See, if you have a cyclic graph simply means that contains at least one cycle. This contains at least one cycle. This contains at least one cycle. Okay. So this contains at least one cycle. For example, this graph, if you notice, okay, A, B, C, D, A, F, G, H. This graph is cyclic because there is at least one cycle. This is your cycle. There is at least one cycle. So this is cyclic graph. Tell me one thing. In this cyclic graph, from vertex A to vertex C, how many paths you have? How many AC paths are there? How many paths are there from A to C? Either you have this path or you have this path. So there are total two paths. So whenever you have a cyclic graph has at least one cycle. In a cyclic graph, you have at least one cycle. There will be at least one cycle. There will be at least one cycle in a cyclic graph. There can be something extra, like, okay, there can be some extra things, but there is at least one cycle. And tell me one thing. If I start at any vertex here, then to this vertex, how many paths you have? From this vertex to this vertex, how many paths will be there? There will be two paths. This will be your path 1 and this will be your path 2. Okay. So what I can say that a graph is cyclic if there is at least two vertices, which have more than one path between them. A graph is cyclic if you have at least two vertices, which have more than one path between them. That is the definition of cyclic graph. Is this clear? Because if I have acyclic, for example, if I give you this graph, Let me give you this graph. In this graph, tell me, do we have any two vertices which have, like in this graph, can you notice every two vertices have at most one path? This graph is actually acyclic. There is no cycle, acyclic. Every two vertices have at most one path. Yes or no? Every two vertices have how many paths? Tell me. Have at most one path. Have at most one path. So this is the idea. I hope this concept is clear. So what is a cyclic graph? There are three definitions. For cyclic graph, we have three definitions. Graph containing at least one cycle, or I can say at least two vertices, or I can say at least two vertices which have more than one path. Or another definition means you start at some vertex, you can follow a non-empty trail, and you can come back without repeating edges. You can come back. Okay. So these are the three definitions of cyclic graph. Any definition you can use, whichever definition you understand. And what is acyclic graph? Acyclic means there is no cycle. Graph containing no cycle. Or I can say every pair of vertices have at most one path. Every pair of vertices, they have at most one path. Or I can say there is no vertex where you can start and you can come back without repeating edges. There is no vertex where you can start and you can come back without repeating edges. All these definitions, are they clear? Which graph is cyclic, which graph is not cyclic? Cyclic and acyclic graph. Is the definitions clear? Very simple. So in a cyclic graph, remember, cyclic graph has at least one cycle. And I told you that whenever I say cycle, cycle always means either this or this or this. Whenever I say cycle, cycle must have at least three vertices. Whenever I say cycle, it means it must have at least three vertices in a cycle. Okay, they must be in a cycle. At least three vertices in a cycle. At least three. So you can have four vertices also, you can have five vertices also, but you must have at least three vertices in a cycle. Okay. So this is the definition of cyclic graph. Is the concept clear? What is cyclic? What is acyclic? Anyone has any doubt? Third definition is not clear. If you have a cycle, tell me one thing. In a cyclic graph, you have a cycle. Agree? There is a cycle. In a cyclic graph, there is a cycle. You can have something extra. You can have something extra. Okay. But there is at least one cycle. There is at least one cycle. There is at least one cycle. For example, in this graph, there are many cycles. But the point is there is at least one cycle in a cyclic graph. So can I say that there is at least one vertex? Can I say there is at least one vertex where you can start and you can come back without repeating edges? Tell me, in this graph, is there at least one vertex? Is there at least one vertex? For example, consider this vertex. If I start at this vertex, I can come back without repeating edges. I can come back without repeating edges. When is it possible? I can come back without repeating edges. When is it possible? Some vertex, there is some vertex where I can start, I can come back without repeating edges. When is it possible? It is only possible when you have cycle. It is only possible when you have cycle. For example, I can start here, I can come back. Can I start here and I can come back? Tell me, can I start here and I can come back without repeating edges? Without repeating edges? No. So that is the idea. This is the idea. So if you have a vertex, let's assume you have a vertex and I start here non-empty trail I have. Okay, I start here, I can go. And if I can come here without repeating edges, if I can come here, what it means? If I can come here without repeating edges, what it means? It means there is a cycle in the graph. The graph is cyclic. The graph is cyclic. So there should be at least one such vertex. There should be at least one such vertex. So the definition 3 means there is some vertex, at least one vertex where we can start, follow a non-empty trail, and come back without repeating edges. Is it clear now, Manisha? Anyone has any doubt? So this is the definition of cyclic graph. In a cyclic, whenever you have a cyclic graph, then these vertices which are on cycle, they have more than one path between them. These vertices, for example, these two vertices, if you notice, these two vertices have more than one path. This path is also there, this path is also there, so they have more than one path between them. Okay, they have more than one path between them. This is your path 1, this is your path 2. So these vertices which are on cycle, they have more than one path between them. Now the next concept is tree. What is this topic? Tree. So let me see. So let's take a break. After the break, we will start the next topic, that is tree. And this is very important topic, tree. Okay, so let's take a break. Let's take a small break. So we will meet after 3 or 4 minutes. Hi everyone, welcome back. Now let's study what is a tree. So what is this tree? Tree and forest, these are the two things. We have a forest and we have a tree. So tree, remember, tree is connected acyclic graph. If you have a connected acyclic graph, that is called tree. It must be connected. This is very important. This must be connected, this must be acyclic. So connected acyclic graph, then that will be called tree. Okay, these two properties must be there. Connected, acyclic. And what is a forest? What is a forest? Forest is like a collection of tree. Is like a collection of tree. For example, this is a tree. I can say connected acyclic. This is a tree because this is connected and this is acyclic. What is forest in the real world? Forest is basically collection of trees. I can say forest is basically collection of trees. So collection of trees means, for example, I can say this is a forest. This is a forest because you have two trees. This is a tree. For example, this is a tree. This is a tree, and this whole thing is a forest. This whole thing is not a tree. This whole thing, this is not a tree because this is not connected. Okay, so I can say forest is basically collection of trees. So what I can say, forest is acyclic graph. Forest is acyclic graph. So every acyclic graph, another name is forest, and connected acyclic graph, that is a tree. So for example, remember, forest means undirected graph with no cycles, means forest means acyclic. The another name for forest, that is acyclic. Acyclic. For example, this is a forest because this is acyclic. This is also acyclic. So these are the forest. This is a forest, this is a forest, and this is also a forest. This is also forest. And what is a tree? Tree is a connected forest, means connected acyclic graph. This is a tree. This is connected and acyclic. There is no cycle here. Yes or no? Can you notice? Can you notice there is no cycle here? There is no cycle here. So I can say this is tree is connected acyclic graph. So what is a tree? Tree as a graph. These are the properties. Tree as a graph. This should be undirected, connected, acyclic. These three properties must be there. Okay. So for example, you can notice this is a tree because this is a acyclic and connected. Connected acyclic. So I can say this is a tree. This is a tree. And this is forest also. Forest means acyclic. So this is forest also. What about this graph? Tell me. This is also acyclic and this is connected. So this is also tree. And what about this? This is not acyclic. So this is not a tree, not a forest. This is not a tree, not a forest, because there is cycle here. We have cycle in this graph. So this is cyclic. So this is neither tree nor forest. This is forest but not tree. This is forest. This is a forest, but this is not tree. So this is acyclic. There is no cycle here. You don't have any cycle. But this is not tree because this is not connected. Next, what about this graph? Which of them are tree? So tell me which graph is not tree and which is tree? Is this tree? Yes, this is tree because this is connected and this is acyclic. This is tree also, this is forest also. This graph is tree also and forest also. What about G2? What about G2? This G2 is tree also, forest also. This is tree comma forest because this is also connected acyclic. You can notice this is connected and this is acyclic. What about G3? In G3, what do we have in G3? What do you think? What do we have in G3? In G3, we have a cycle. In G3, we have a cycle A, B, D, E. There is a cycle A, B, D, E. So this G3 is neither tree nor forest. This G3 is not a tree and this is not forest. Because we have a cycle. Which cycle we have? See this cycle. A, B, E, D. This cycle we have A, B, E, D. A, B, E, D cycle. So this cycle of 4 length we have. What about this last one? This G4. This is not connected. This is forest. This is forest, but not tree. This is forest, but not tree. Because this is not connected. You can notice this is not connected. This is not connected. There is no cycle. This is acyclic, but this is not connected. and this is another tree with cycle. Okay. Okay. Now let's see. So let's see the next. So what is a tree? You understood what is a tree? Tree is a very simple. So every I can say a graph in which every component is tree, that is forest. Forest means every component is tree. Okay, forest. Remember forest. Forest basically means that every component is a tree. Every component is a tree, that is forest. Okay, so forest means acyclic graph. Forest means acyclic without cycle. And what is the next? In a tree, okay, so I can say, and remember this, in a tree, a vertex of degree 1 is called leaf. Vertex of degree 1, we call it leaf. So which of these graph are tree? G2. G2 is acyclic, right? Priya, G2 is acyclic, and this is connected. Because what you can see, this G2 is like this: C, A, and then there is F, and there is E, and there is B, and there is D. So this is connected also acyclic also. You can notice what you can do. You can see in this what you can do. You can pick this B and you can pull it here. This B you can pull it out. This B you can pull it out. So what you will get? This is what you will get. This graph you can write like this. This same graph you can write like this. The same graph E, B. The same graph you can write like this. Yes or no? Untwist. So just okay, just pick it and pull it here. So you can notice this is acyclic. There is no cycle here. This is acyclic and this is connected. And you can notice this is connected. So this is a tree. Okay, let's see the next. Which of these graph are forest? Which of these graph are tree? So tell me, what about PN? This PN is a tree. Every tree is forest. Every tree is a forest. Every tree is a forest. Because tree means connected acyclic and forest means acyclic. This means acyclic. Tree means connected acyclic. So yes, this is a tree. What about this? This is none. Okay, not forest. This is not a forest. So not forest, so not tree. If this is not forest, so this is not tree. What about KN? Neither forest, not tree. Not forest, not tree. Not forest, not a tree. When it will be tree? Tell me when this KN will be tree? This KN will be tree if and only if n equal to 1 or 2. If and only if n equal to 1 or 2. Okay. So when your number of vertices is 1 or 2, then it will be tree. Else it will not be tree. Okay, next. So you can notice this is connected. So this is tree. This is also tree. This is also tree. Okay. Oh, so this is one graph with 3 connected components. So this is a forest. This is a forest, but this is not a tree. Remember this whole this graph. Look at this graph. This graph is forest but not tree. Example of forest. Now few very important things. Remember very important things. Let's see. So what is a tree? Complete analysis of tree now we will do. And this is important. Complete analysis of tree. So you know the first thing is very important. That is tree means connected. It should be connected. It should be connected and it should be acyclic. These two things must happen. Connected it should be and it should be acyclic. Because acyclic means forest. Acyclic means forest. So connected forest is basically tree. Okay, undirected. Yes, undirected. Okay, so tree is undirected. This is undirected. Okay, so connected acyclic undirected graph, that is your tree. Now the second thing, how many edges? What is the number of edges? Like what is the number of edges in tree? So if you have a tree on n vertices, so if you have a tree on n vertices, if you have a tree on n vertices, for example, if you have a tree on 4 vertices, then what will be the number of edges? See, you can find like this. Okay, what is a tree? Tree means connected acyclic. This is a connected acyclic. So you cannot bring cycle. Remember, you cannot bring cycle. You cannot bring cycle. So let us assume you have n vertices. You have n vertices. So what we have to do? So this is your vertex. So okay, you want to create n vertices. Then let's see how many edges will come. Let's see how many edges will come. So this is induction. This is the proof by induction. What I'm doing, I'm starting with A1. This is proof by induction. When I have one vertex, then how many edges? Number of edges. When I have one vertex, then how many edges? When I have one vertex, number of edges is 0. Okay. Now, if I have two vertices, then is it tree? Is this tree? When I have two vertices, is this tree? Is this tree? No, this is not tree because this is not a tree. This is not tree because this is not connected. So how many edges I want? So one edge. Let me add three vertices. If I have three vertices, then how many edges I need? Is this tree? This is not connected. Is this tree? Yes. But can I do this? Tell me, can I do this? No, because now there is a cycle. So I cannot do this. So with three vertices, you will definitely get two edges. Okay, let me add one more vertex. Let me add one more vertex. See, tell me, if I add like this, is it a tree? How many edges I want? Tell me, if I add this vertex, to add this vertex, how many edges I need? I want to add this vertex, how many edges I need? Can I use two edges? Can I use two edges? Can I use two edges? No, because now there is a cycle. Now there is a cycle. Can I use two edges? No, because now there is a cycle. So at most one edge I can use. For example, I can do this, or I can do this, or I can do this. So if I have four edges, four vertices, then there are three edges. So the idea is very simple. The idea is very simple like this. If you have n vertices, then there will be n minus 1 edges. Okay, so number of edges in tree, that will be equal to number of vertices minus 1. This will be the number of edges in a tree. Is this clear? Because if I add one more, for example, tell me, if I add one more vertex, then can I add two edges? Can I add two edges? Like, can I add two edges? Tell me, can I add two edges? No, because if I add two edges, there will be a cycle, and I want a tree. Tree means connected acyclic. So can I? Okay, so this is the idea. So to add this vertex, I need only one edge. So if I have four, then it will be five, then four. So number of vertices is n. If your number of vertices is n, then number of edges will be n minus 1. Okay. Yes, this is a tree. Is this a tree? Tell me. This A1, is this a tree? This A1, A2, is this a tree? Let's see, graph G1, graph G2. Yes, this is a tree. Tree means connected acyclic. This is connected also acyclic also. This is connected also acyclic also. Just use the definition, Manisha. Tree means connected acyclic. Use the definition. Check, is it connected? Check, is it acyclic? These two things you check. Connected check, acyclic check. So number of edges in a tree, that will be number of vertices minus 1. Tell me one more. Hi everyone. Am I audible? Okay, so there is some electricity issues. Anyway, let's start. So what I was saying, so this is the idea. Now tell me, this is my question. If you have n vertices, okay, you have graph with n vertices, n minus 1 edges. Can I say this is a tree? Graph n vertices, n minus 1 edges. Does it imply tree? Graph n vertices, n minus edges. Does it imply tree? Does it imply tree? Graph with n vertices, n minus 1 edges. Does it imply tree? So the answer is no. The answer is no. Because, for example, consider this graph. A, B, consider this graph. A, B, C, D. Consider this graph. In this graph, you have how many? In this graph. Okay, so what you can do, you can take this graph. Take this graph. So in this graph, you have n equal to 4 and number of edges equal to 3. Is this tree? But not tree. But not tree. So please don't make this mistake. Okay, if you have, remember, if you have tree, then there will be n minus 1 edges. N minus 1 edges does not mean tree. Okay, is this clear? This is not a tree. You have four vertices and 3 edges. So, but still this is not a tree. So remember, if you have a tree, okay, if you have a tree, then it means number of edges will be this. If you have a tree, then number of edges will be this. But if your number of edges is this, then it does not imply tree. Is this clear? Is this point clear? So in every tree you have n minus 1 edges. Now let's see one interesting thing. Tell me one thing. This is my question now. You have a connected graph. You have a connected graph. Now you have a connected graph on n vertices. You have a connected graph on n vertices, n minus 1 edges. Does it imply tree? Connected graph on n vertices, n minus 1 edges. Does it imply tree? Tell me. Now the answer is yes. Now the answer will be yes. Why? Because now you have a connected graph on n vertices. So your graph is connected on n vertices and you have n minus 1 edges. For example, if you have n vertices, like, okay, for example, if you have 4 vertices and you have, like, these are the 4 vertices. Now create a connected graph with 3 edges. How will you create connected graph with 3 edges? Okay, so n vertices, n equal to 4, create a connected graph. Create a connected graph with 3 edges. With 3 edges. So tell me, if you create a connected graph with 3 edges, can you bring cycle? Can you bring cycle? Can you bring cycle? No, because if I bring cycle, then it is not connected. If I bring cycle, then it is not connected. So let's create a connected graph with 3 edges. Let's create. Okay. So what you have to do? You will get a tree, right? You will definitely get a tree. Is this clear to everyone? So remember, connected graph with n. If you have a, so I can say this is another definition of tree. So tree has these definitions. The first definition of tree is connected acyclic. This is the first definition of tree. Connected acyclic. Okay, this is the first definition. What is another definition? Tell me what is another definition. Connected with n minus 1 edges. Connected with n minus 1 edges. This is another definition of tree. Now let's see one more thing. Tell me one more thing. If I say, okay. Okay, tell me one more thing. No problem. You will get a Sandeep, you will get a tree. The point is simple. The point is you will get a tree. You can create whatever you want, you will get a tree. Whatever connected graph you create, connected graph you create with 3 edges. connected graph you create with 3 edges, you will get, okay, you will get this, right? Now my question, this is another question. Is this maximally acyclic? Is the following graph maximally acyclic? Is this maximally acyclic? Is this maximally acyclic? I am asking, maximally acyclic. Is this maximally acyclic on 5 vertices? On 5 vertices. The following graph. So I am giving you a graph and you tell me, is this graph maximally acyclic on 5 vertices? So number of vertices is fixed. You can't change the number of vertices. So let me give you this graph. C, D, E. First you tell me, is this acyclic? First you tell me, is this acyclic? Yes, this is acyclic on 5 vertices. Can I say this is maximally acyclic on 5 vertices? Can I say this is maximally acyclic? Can I say this is maximally acyclic? Maximally acyclic. Can I say this? On 5 vertices, can I say this is maximally acyclic on 5 vertices? The answer is no. The answer is no. This is not maximally acyclic on 5 vertices. Why? This is acyclic. But with 5 vertices, you have 5 vertices, you have a scope. Yes or no? You can add something and it still will be acyclic. Yes or no? This is not maximally acyclic. Why? Because you can add this as and still this is acyclic. Still this is acyclic. Is this clear to everyone? So what is maximally acyclic forest? This is my question. What is maximally acyclic? Maximally acyclic. Maximally acyclic graph on n vertices. What is that? Maximally acyclic graph on n vertices. That is your tree. Tell me, now is this maximally acyclic? Is this maximally acyclic now? Now is it maximally acyclic? Can you do something? Can you add something more? Now there is no scope to add. Very good. Manisha, very good. Now there is no scope to add. Now this is maximally acyclic. There is no scope. There is no scope. So now this is maximally acyclic. Now this is maximally acyclic. Okay. Now maximally acyclic. I can say now this is maximally acyclic. So this is your definition, that maximally acyclic graph on n vertices, that is a tree. This is another definition of tree. Yes, this is a forest. Every tree is a forest. So these are the definitions of tree. Remember, these are the definitions. There are many definitions of tree, and all these are very important. We will solve a question, TIFR question we will solve, and this is very important. So what are the definitions of a tree? T is a tree. This is one definition. What is another definition? See, what is another definition? Another definition is exactly one path. See, what is the definition of acyclic graph? Tell me, what is the definition of forest? Forest means acyclic graph. Forest means acyclic graph. And what is the definition of that? What is the definition of that? That is, between any two vertices, you have at most one path. Between any two vertices, we have at most one path. We have at most one path. This is the definition. Now tell me, if we have between any two vertices, if you have exactly one path, then what will you say? Between any two vertices, if you have exactly one path, between any two vertices, does it imply connected? Does it imply connected? Does it imply connected? Tell me. Between any two vertices, whatever two vertices you take, you have exactly one path. Exactly one path. So this is connected. And because you have exactly one path, so this is acyclic. Because you have exactly one path, so this is connected acyclic. So now this is the definition of tree. Now this is the definition of tree. So tree means a graph in which between any two vertices, you have exactly one path. This is the definition of tree. Remember, forest definition says that You have at most one path between any two vertices. You have at most one path. For example, you can take this A, B, C, D. You can take this graph. You can notice between these two vertices, one path. Between these two vertices, there is no path. What is the definition of tree? Means any two vertices have exactly one path. So this is another definition. Any two vertices are connected by unique path. And what is another definition? Maximally acyclic. Means you cannot add some more. In a tree, if you add one more edge, then what will happen? Tree plus one more edge. Tree plus one more edge. What that means? In a tree, if you add one more edge, then what it means? Then it means cyclic. You will get a cyclic graph if you have a tree, because in a tree there is no scope to add one more edge. For example, this is your tree. In this tree, if you add one more edge, whatever edge you add, whatever, that is your choice. So if you add one more edge, any edge, if you add one more edge, any edge, okay, then that will be cyclic graph. Okay, so this is the idea. So I can say that tree is maximally acyclic, means you cannot add any new edge, and tree is minimally connected. Why tree is minimally connected? Because see, can I say this graph is minimally connected? Like, is this graph minimally connected on four vertices? Is this graph minimally connected? Minimally connected, because we basically want connected. This is what we want, but we want minimally connected. Is this graph minimally connected on four vertices? My question. So for example, this is a graph I am giving you, A, B, C, D. Is this graph minimally connected? Tell me. Minimally connected. Remember, we want connected, but we want minimally connected on four vertices. Minimally connected means with minimum number of edges. Minimally connected means with minimum number of edges. So the answer is no, because what you can do, you can remove this, still it will be connected. You can remove this, still it will be connected. You can remove this, still it will be connected. Yes or no? Now tell me, is this minimally connected? Now is this minimally connected? Yes, now this is minimally connected. Now if you remove one edge, then it is not connected. Now this is minimally connected with minimum number of edges. So remember, tree means connected with minimum number of edges. So this is the definition of tree. Tree means connected graph with minimum number of edges. Connected with minimum number of edges. With minimum number of edges. That is the definition of tree. Okay, connected with minimum number of edges. Okay, so this is your another definition, minimally connected. This is another definition we have already seen, connected and these many edges. Also acyclic with these many edges. Okay, is this clear? This we have already seen, maximally acyclic. Maximally acyclic. Tree is maximally acyclic. Tree is acyclic. Tree is acyclic with maximum number of edges. Tree is acyclic with maximum number of edges. Yes or no? See, tree is connected with minimum number of edges, and tree is acyclic with maximum number of edges. Yes or no? Tree is acyclic with maximum number of edges. For example, if I give you this graph, like these two vertices I give you, and if I ask you, create acyclic with maximum number of edges, you need to create acyclic. And you need to put maximum number of edges. Then what you will do? Can you do this? No, you cannot do this. Your task is acyclic. Is it correct? Okay. Is this acyclic with maximum number of edges? Is this graph acyclic with maximum number of edges? No, I can do this. Is this graph acyclic with maximum number of edges? Is this graph acyclic with maximum number of edges? Yes. Now this is acyclic with maximum number of edges. So is this clear? Definition of tree. All the definitions of tree. Tree is connected with minimum number of edges. Tree is acyclic with maximum number of edges. or I can say tree is connected with n-1 edges, or tree is acyclic with n-1 edges. These are the definitions. These are all the definitions of tree. All these are clear. So tell me, which of these definitions are of tree? Which of the following is a definition of tree? Which of the following is a tree? Acyclic graph. Can I say this is tree? Acyclic graph. No, because acyclic graph means forest. That means forest. Connected graph. Can I say connected graph is tree? No, because connected graph can have cycle. Connected graph can have cycle. And acyclic graph can be like this. Acyclic graph can be like this. And what about this acyclic connected graph? Acyclic connected graph. Yes, this is correct. Acyclic connected graph. Connected graph with minimum number of edges. Connected with minimum number of edges. Yes, this is correct. Connected with minimum number of edges. Minimally connected. Minimally connected. Yes. Okay. So this is the definition. Tell me, which of them is tree? Which of the following is a tree? Which is a tree? N vertices graph with n-1 edges. N vertices graph with n-1 edges. No, we have already seen. What is the counterexample of this? For example, consider this graph. Consider this graph. Here n equal to 4 and number of edges equal to 3. So this graph is not tree. N vertices connected graph with n-1 edges. Yes, this is correct. Connected graph. Maximally acyclic. Yes, this is correct. Every two vertices have unique path. This is correct. All these definitions, are they clear? Please tell me. All these definitions. So remember, tree is connected with minimum number of edges. Tree is acyclic with maximum number of edges. All these definitions are very important. So what is a tree? Tree is connected graph with no cycles. There is no cycle. Connected with no cycle. Acyclic. Connected acyclic. Forest acyclic. Path are trees. Every path is a tree. Star is also a tree. This is star graph. I told you the star graph means K1, N. This is the star graph. So you can notice every star graph is also a tree consisting of one vertex adjacent to all other. Tell me about this question. Is this true? Every tree with at least two vertices has at least two vertices of degree 1. How to prove it? What do you think? What is coming to your mind? Like, to prove this, what is coming to your mind? To prove this. To prove this, what is coming to your mind? Degree sum formula. Degree sum formula. Yes or no? Degree summation. What is degree summation of tree? Degree summation of tree. What is degree summation of tree? So what is total degree? Summation of degree of all the vertices. What that will be? For all the vertices. That will be equal to twice the number of edges. And number of edges will be n-1. Okay. So this is the idea. So I can say, remember, in a tree, total degree is equal to 2 into n-1. In a tree, total degree is equal to 2 of n-1. So every tree, how to prove this? Every tree with at least two vertices has at least two vertices of degree 1. Prove by contradiction. Just prove by contradiction. Yes or no? Let's prove by contradiction. Let us assume that you don't have this. Assume you don't have at least two vertices of degree 1. Assume you don't have. Assume we don't have at least two vertices of degree 1. At least two vertices of degree 1. What it means? So, okay, remember you have a tree. So basically you have a tree and number of vertices is greater than equal to 2. You have a tree with the number of vertices greater than equal to 2. I'm assuming you don't have at least two vertices. What it means? It means number of degree 1 vertices. It means number of degree 1 vertices. Degree 1 vertices that is less than equal to 1. Number of degree 1 vertices. How many vertices have degree 1? So number of degree 1 vertices is less than equal to 1. Now you apply the degree sum formula. Okay. Tell me one thing. In a tree, every vertex has degree what? Because it is a tree, so it is connected. Because it is a tree, so it is connected. So every vertex has degree what? Every vertex degree is what? Every vertex degree is greater than equal to 1. Because you cannot have isolated vertex, because every tree is connected. So every vertex has degree greater than equal to 1. Now what you have? Total n vertices you have, a1, a2, total n vertices you have. And in these n vertices, I am assuming that number of 1 degree vertex is only at most 1. What it means? Tell me what it means. It means number of vertices whose degree is at least 2. With the degree at least 2, what is that? Number of vertices with the degree at least 2, what is that? With the degree at least 2, what is that? That is greater than or equal to n minus 1. Yes or no? Yes or no? Degree 1 vertices, I am assuming that degree 1 vertices are not 2. You don't have, assume we don't have at least 2 vertices of degree 1. This is what I am assuming, that we don't have at least 2 vertices of degree 1. It means degree 1 vertices is less than equal to 1. But you know that every vertex has at least 1 degree. Every vertex has at least 1 degree. So tell me, number of vertices with degree at least 2, what is that? That is greater than equal to n minus 1. Now tell me the total degree. Now tell me the total degree. Now the total degree will be equal to what? That will be equal to n minus 1 vertices have degree at least 2. N minus 1 vertices. So total degree will be greater than or equal to this. And the remaining vertex have degree 1. The remaining vertex, what I'm saying, so at most 1 vertex has degree 1. At most 1 vertex. So n minus 1 vertices have degree. Okay. So finally, this will be the idea. So total degree will be greater than equal to this. But total degree in a tree should be equal to this. What is not clear? Please tell me. So there is a contradiction. There is a contradiction here. See. Okay, one by one, let me see. Just check this. The question is this. First, you understand the question, please. Okay, so let's focus on the question. The question is this, that you have a tree with the number of vertices is greater than equal to 2. You have this. And we have to prove. What we have to prove? We have to prove that at least 2 vertices have degree 1. At least 2 vertices have degree 1. Have degree 1. Have degree 1. So tell me, this is what I want to prove. Tell me few things. Actually, for contradiction, what it means? If I want contradiction, then what it means? Tell me, if I want contradiction, for contradiction, what I will assume? Let me know. For contradiction, what I will assume? This is what we have to prove. At least 2 vertices have degree 1. At least 2 vertices have degree 1. So for contradiction, what I will assume? Assume degree 1 vertices. Degree 1 vertices. How many degree 1 vertices? So number of degree 1 vertices is less than equal to 1. Yes or no? Is this clear? Because we have to prove this, that at least 2 vertices have degree 1. So for contradiction, I will assume that number of degree 1 vertices is less than equal to 1. So tell me, in a tree, tree is connected. Tree is connected or not? Tree is connected, and n is already greater than equal to 2. Number of vertices is greater than equal to 2. So tree is connected graph with the number of vertices greater than equal to 2. You have, this is given. This is given, tree is connected. So what I can say, what can I say about degree of V? That is greater than equal to 1 for all vertices, right? For all vertices in the tree. This is correct. Every vertex, because this is connected, so every vertex should have degree greater than equal to 1, because this is connected. So you cannot have isolated vertex. You cannot have isolated vertex. You cannot have degree 0 vertex. So every vertex should have degree greater than equal to 1. Now see this, number of 1 degree vertices is less than equal to 1. All vertices have degree greater than equal to 1. So how many vertices have degree greater than equal to 2? Are you getting my point? So we have number of degree 1 vertices. Number of degree 1 vertices is less than equal to 1. All vertices have degree greater than equal to 1. All vertices have degree greater than equal to 1. So tell me the number of vertices with the degree, number of vertices with the degree greater than equal to 2. Tell me, with the degree greater than equal to 2. With the degree greater than equal to 2. What is that? Number of vertices with the degree greater than equal to 2. That will be greater than equal to n minus 1. Yes or no? Total n vertices you have. Total n vertices you have. Number of vertices which have degree 1, that is less than equal to 1, means at most one vertex has degree less than equal to 1. All vertices have degree greater than equal to 1. So number of vertices with degree greater than equal to 0, that is at least n minus 1. So now what can I say about total degree? What can I say about total degree? Arey yaar, A1, A2, A3. Let us assume this vertex has degree. Let us assume this vertex has degree less than equal to 1. Means this vertex has degree 1. Because this vertex has degree 1. Because, okay, this vertex has degree 1. And these vertices have degree what? These vertices have degree greater than equal to 2. Yes or no? Because this is our assumption. So this vertex has degree equal to 1 and these vertices have degree greater than equal to 1. Then now what? Now what? Now total degree will be equal to 2 into n minus 1 plus 1. That is because of n minus 1 vertices. That is because of the one vertex. That is because of n minus 1 vertices. And this is a contradiction. And this is a contradiction. This is a contradiction, right? This is a contradiction. Is this clear? So every tree with at least 2 vertices has at least 2 vertices of degree 1. Every tree with at least 2 vertices has at least 2 vertices of degree 1. Or I can say every tree with at least 2 vertices has at least 2 leaf vertices. Okay? Is this clear? The next concept is directed acyclic graph. What is directed acyclic? It simply means this is a directed graph in which there is no cycle. Directed graph without cycle. Is this directed acyclic graph? DAG. In short, we will write it DAG. So tell me, is this directed acyclic graph? This is not directed acyclic graph, right? Because there is a cycle. You can notice there is a cycle here. There is a cycle. There is cycle here. There is a cycle. Or you can see there is cycle here also. For example, there is cycle like this. There is a cycle like this. From A you can go to F. From F you can go to D. From D you can go to A. So this is cycle. So this is not a directed acyclic graph. Okay, you have cycle. So this is not a directed acyclic graph. What about this graph? A, B, C, D. What about this graph? What about this graph? This is also not a directed acyclic because there is a cycle here. What about this graph? A, B, C. What about this graph? What about this graph? This is directed acyclic. There is no cycle here. You don't have any cycle. You can go from A to B, B to C, but you cannot go from C to A. What about this graph? What about this graph? This graph is also not directed acyclic. This graph is also not. Okay. So directed acyclic graph, DAG, means directed graph that has no cycle. So for example, this is your DAG. This is directed acyclic. You can go from 1 to 4 from this you can do, but you cannot go from 1 to 5. See, you can do this, but you cannot do this. What about this? This is also directed acyclic graph. You can check. This is also directed acyclic graph. You can check. There is no cycle. See, you can go from A to B, from B to C, from C to G, but you cannot go from G to A. You cannot go from G to A. So this is also DAG. There is no cycle. You can check. There is no cycle. This is directed acyclic. There is no cycle. See, you can go from B to E, from E to D, from D to C, but you cannot go from C to B. So there is no cycle here. This is also directed acyclic. You can check. There is no cycle. Here also there is no cycle. You can check. Very simple. There is no cycle here also. For example, you can go from 6 to 5, from 5 to 3, but you cannot go from 3 to 4. This is also directed acyclic. You can check. There is no cycle. You can check everything. You can check. There is no cycle. Okay. And the next concept is rooted tree. What is this rooted tree? Rooted tree is a special type of directed acyclic graph. Remember, remember one thing you remember, rooted tree is a directed graph and tree is undirected graph. Remember, tree is undirected graph. This is an undirected graph and rooted tree is a directed graph. This is a special type of directed graph. This is a special type of directed acyclic graph. This rooted tree, remember, this rooted tree is very misunderstood concept. This is a special type of directed acyclic graph. A special type of directed acyclic graph. Let me tell you one thing. This rooted tree has many students have misconception. This rooted tree, this is misunderstood by majority of students. This is misunderstood by majority of students. Let me tell you, majority of students, they don't even understand this this rooted tree. They don't really understand this. Okay, so let's see what is this rooted tree. Remember, rooted tree is like this. The definition of rooted tree is simple. What is a rooted tree? Rooted tree is a directed acyclic graph. First of all, it is a directed acyclic graph with a root, and there are some other conditions. There are some other conditions, plus some more conditions, plus unique path, plus. So remember, rooted tree is a directed acyclic graph with a root and unique path from root to any vertex. Unique path. This is important. Please understand. Unique path from root to every other vertex. From root to every other vertex. With example, let's see. Is this okay? Basically, you have a root. This is your rooted acyclic graph. Sorry, this is your rooted tree. Your rooted tree has a root. There is a root. There is a root. So there is a one vertex which is root, and other vertices are like this, and other vertices are like this. Okay, so this type of graph, C, D, E. Okay, this type of graph is called rooted tree. So in a rooted tree, you have one vertex which is root. You have one vertex which is root, and this is directed acyclic graph. You can notice there is no cycle. So there is root, and you can notice this is directed acyclic. There is no cycle. And also from root to every other vertex, there is unique path. You can notice from root, unique path from root to every other vertex. You can notice from root to this vertex, there is a unique path. From root to this vertex, there is a unique path. This is the definition of rooted tree. Is this clear? So tell me, is this a rooted tree? This is a rooted tree. Is this a rooted tree? This is also a rooted tree. Rooted tree means there is a root, acyclic, and from root to every other vertex, there is at most one path. At most one path. Is this a rooted tree? A, B, C, D. Is this rooted tree? Is this rooted tree? There is root. There is root. Acyclic also, but which condition is not satisfied? Which condition is not satisfied? This is directed acyclic also, root also. Which condition is not satisfied? Unique path. We don't have unique path from A to D. We don't have unique path from A to D. We don't have unique path from A to D. The definition is clear. Please tell me. This is the definition of rooted tree. Directed acyclic graph with root. There is a root and unique path from root to every other vertex. So you have root, from root to every other vertex, there is a unique path, and it is directed acyclic. You can notice this graph is directed acyclic, but you don't have unique path from root to every other vertex. Actually, rooted tree, how you can create? For example, in a rooted tree, one vertex is created as root. For example, if I create this vertex as root, like this is your normal tree, this is your normal tree, and this is the rooted tree. This tree is normal. I can say this is your tree. This is a normal tree, which is an undirected graph. Which is an undirected graph. Okay, so this is a normal tree, which is undirected graph, and this is a rooted tree, which is a directed graph. This is a rooted tree, which is a directed acyclic, special directed acyclic, special. Okay, so what you can do, if you create this, for example, if you create this as root, then these will be the children. These will be the children. Okay, this is not rooted tree. This is not rooted tree. Tell me, is this rooted tree? A, B, is this rooted tree? This is not rooted tree because you don't have root. There should be unique root. You should have unique root. Okay, so these are the properties of rooted tree. In a rooted tree, what we have? In a rooted tree, we have a unique root. You must have a unique root. Second, it must be a directed acyclic graph. There should be no cycle. And third, from root to every node. From root to every node, to every other node, you have unique path. These three things, this is the definition of rooted tree. These three things must happen. This is not a rooted tree because you must have unique path. You must have unique this what I'm saying, unique root. Okay, so this is the difference. Remember, directed acyclic graph and rooted tree, they are different. Rooted tree is a special type of directed acyclic graph. So you can notice these are the properties of a rooted tree. There is exactly one node. There is designated node who is root, and this is directed graph. This is directed graph, directed acyclic graph, and from root to any node there is exactly one path. So remember, this is directed acyclic graph. This graph is directed acyclic, but this is not rooted tree. Okay, all these points, are they clear? For example, this is not a rooted tree. Why this is not a rooted tree? This is not a rooted tree. This is not rooted tree because there is no path from R to C. There is no path from root to C. There is no path, but from root to C there should be exactly one path. Okay, and let me tell you that rooted tree, for convenience, we draw without direction. For example, if I want to draw this rooted tree, you can notice this is a rooted tree. A, B, C, D. This is a rooted tree. But for convenience, what we do? For convenience, this is only for convenience. For convenience, what we do? We draw without direction. We draw without direction for convenience. But tell me, remember the directions are like this. The directions are like this. So for convenience, we draw without directions. For example, in linked list, okay, analogy, like if you want analogy, then for example, you study this binary tree structure, you study, right? This binary tree data structure you study. This data structure you study, binary tree data structure. What happens there? There you have this type of node. Every node is actually like this. There is a left pointer, there is a value, there is a right pointer. Yes, correct. Every node is like this. Every node is a structure. Every node is a structure. There is a value. Okay. So like this you have. And for convenience, what we do? For convenience, what you do? You directly write like this. But actually, what happens in the computer? Actually, what happens? This is the actual thing. This is the actual thing. This is what actually happens in the computer. And this is for convenience. This is for convenience. Okay. Is this concept clear? Rooted tree. The concept of rooted tree. So this is the actual thing. This is the actual thing. And this is for convenience. For convenience, we remove the directions. Now let's see some terminology in the rooted tree. In the terminology. Okay. So if you have this rooted tree, so for example, this is your root A, B, C, D, E, F, okay, G. So let's assume this is your graph. This is your rooted tree. Tell me what is root. First, to tell me what is root. Root is R. Okay. These are called children of root. These are called children of root. So what are the children of root? These are called children of root. So the children of root are A, B, C. These are the children of root. What are the children of B? What are the children of B? Children of B are E, F. These are the children of B. And remember, like this is the parent. I can say, what is the parent of C? What is the parent of C? That is R. What is the parent of C? That is R. Okay. Tell me one more thing. So the parent of C is R. What is parent of G? That is F. The parent of G. So for this G, parent is F. Okay. So like this is the parent, these are the child. This is the parent, these are the child. This is the parent, these are the child. This is the children, this is the parent. Okay. This is the children, this is the parent. Now, these, okay, what do we call them in your life? Like this is the parent, these are the children. What they are for each other? What they are for each other? They are siblings. Okay, so I can say, what are the siblings? What are the siblings of B? A, C. These are the siblings of B. What are the siblings of F? What are the siblings of F? E is the sibling of F. Because these are the common parent. They have the common parent. They have the common parent. Okay, what are the siblings of D? What are the siblings of D? None. None. There is no sibling of D. Okay, clear? So these are the terminology. Next we have something called ancestors. Okay, who are the ancestors of C? Like if I ask you, what are the ancestors of C? Tell me, what are the ancestors of C? So that is R, only R. R is the ancestor of C. What are the ancestors? What are the ancestors of G? What are the ancestors of G? Ancestors of G. So that will be F, that will be B, that will be R. F, B, R. Yes or no? Correct. So the ancestors, because for G, this is the ancestor, this is the ancestor, this is the ancestor. So these are the ancestors of G. So this is the terminology. All these terms, are this clear? So what is a root? What are the children? What are the siblings? These are the children of U. Okay. Leaf, leaf. Okay. And anyway, now after this, so what is a path? Tell me, what is a path from A to G? What is path from A to G? You have unique path because it is rooted tree. Because it is rooted tree. So what is path from R to F? What is path from R to F? So that will be like this: R to B, B to F. Okay, so this is path from R to F. So you will have a unique path from root to every other vertex. From root to every other vertex, you have a unique path. Correct? So, for example, what is path from B to G? What is path from B to G? So that will be B to F and F to G. There is a unique path. You will always get a, like from root to any other vertex, you will get a unique path. From root to any other vertex. Okay. The next concept is height and depth of a node. What is the height? See, what is the, these are the two concepts. What is the height of a node and what is depth of a node? Tell me, just in the real life, when you say that you are on a height, this word height, when you use this word, when you are on the top of a building, like this is your building, when you are standing here, then what you will say? Then you will say, I am at a height. Yes or no? What you will say? You will say that I am height h. This you will say height h. Yes or no? From here you will see and you will say that this is height h. Agree? Correct or not? And when do we use this word depth? This word you, okay, so this is your building. Let's assume this is the building. And when this word, when we use depth, this word we use when you are in a wall. So let's assume there is a kuwa, you know, wall, and you are here. Now you are looking up. You are looking up. Your eyes are looking up. Then what you will say? You will say that this is the depth. Basically, this is the depth. Correct? Yes or no? Is this clear to everyone? So basically, height of a node and depth of a node. If I ask you height, your height, then you will look below. Yes or no? If I ask you what is your height, then you will look below. And if I ask you what is your depth, you will look above. Yes or no? So for example, in this same graph, now in this same graph, let me take in this same graph what is height and what is depth of all the nodes. So what is the height and what is the depth? So remember, if I ask you the height of R, then you will look below. If I ask you what is the height of R means you will look below. This is the longest. The height of R will be the longest, farthest leaf. This will be the, okay, remember these are the leaf nodes. These are the leaf nodes. This is a leaf node. This is a leaf node. This is a leaf node. And this is also a leaf node. Because they don't have children. Leaf node means they don't have children. And these are internal nodes. These are internal nodes which have children. These are internal nodes which have children. So tell me, what is the height of R? If you want to check height, then where will you see? You will look below. Yes or no? Tell me. So let me connect other network. Hello, am I audible? Okay, so tell me, if you want to find height of R, then you will look below. What is the longest path? Tell me what is the longest path, like this. Height means number of edges. So number of edges is 3. Height means number of edges. This is also number of edges below. This is number of edges below. And this is number of edges above. Okay. So it is like this, number of edges. So this is the longest path. So number of edges is 3. And what is depth of R? What is depth of R? That is 0, because you will look above. The depth of R is 0. R is not at the depth. What is the height of A? Height of A, that will be 1. Height of A, that will be the longest path to some leaf, that is 1. What is depth of A? That will be 1. What is depth of, height of G? Height of F. What is height of F? That will be 1. What is depth of F? That will be 2. Is this clear to everyone? Please tell me. The concept is clear. For example, what is height of G? Height of G 0. Depth of G 3. So what is height? Height of a node in rooted tree. You have a rooted tree. In a rooted tree, what is height of a node? And what is depth of a node? So height of a node is basically from the node. You have a node X. So from X to the farthest leaf. From X to the farthest leaf. Farthest leaf. Okay, from X to the farthest leaf, number of edges. So this will be your height of a node. And what will be depth of a node? What will be depth of a node? That will be from R to X, from root to X, from root to X, number of edges, from root to X, number of edges, to X, number of edges. Is this clear? Like here, if I ask you, for example, what is height of D? Height of D means from D to farthest leaf, that is 0. But depth of D, that is R to D. R to D, that is 2. Okay, tell me, is this concept clear? Height and depth. Concept clear? So what are the internal nodes? Internal nodes which have at least one children. Internal nodes have at least one children. And leaf nodes, they don't have any child. So remember, this is the definition of leaf node. Leaf node means node without child. Node without child. There is no child, then it will be called leaf node. And internal node simply means at least one child. Internal node, that simply means node with at least one child. Node with at least one child. Okay, tell me, if I give you this graph, if I give you this rooted tree, then tell me, is this leaf node or what? So you know this is root node. Is this leaf node or internal node? What you will call it? Is this root node or see, this is root node. This is leaf. This is not internal node. This is not internal, because internal node means at least one child. Okay, so this is the definition. Internal node means node with at least one child, and leaf node means node without child. Okay, so these are the siblings. These are the children of you. These are the internal node. These are the internal nodes. These are the internal nodes. Okay, these are the internal nodes. These are the leaf. Like, okay, this you can notice yellow. Yellow is the leaf, and white ones are the internal nodes. This is the parent of W. This is the path from root to W. This is the path from root to W. Okay, so all these definitions we have seen. So for example, this question you can notice. Suppose that u comma v are siblings in a rooted tree. Which statement are true? U comma v are siblings. Siblings means same parent. Sibling means same parent. So tell me, If they are siblings, then what? They must have the same ancestors. Is it correct? Is this correct? They must have same ancestors. Yes, this is correct because they have same parent. They have same parent, so they have same ancestors. They have a common descent. They have a common descendant. This is not true. For example, here you can notice that 4 comma, these are siblings. You can notice these are siblings. They don't have common descendant. The descendant of 9 are these. These are the descendant of 9. And these are the descendant of 4. They don't have common. If U is a leaf, V must be a leaf. No. Okay, this is also false. So this now. The remaining things we will see in the next class. But the concept of rooted tree is very like misunderstood concept. Let me tell you. This rooted tree concept. Many people, they don't really understand rooted tree. Okay, remember, rooted tree is not an undirected graph. First of all, rooted tree is not a tree. Tree, remember the difference between tree and rooted tree. What is that? What is the difference between tree and rooted tree? So the tree is undirected graph and rooted tree is directed graph. So this is the difference. This tree is undirected. This is undirected and this is directed. Here you have concept. Here you have concepts like these concepts you have here. What is the, okay, so this is root, this is undirected graph, this is directed graph. Here you have something called root. These concepts you have in this rooted tree. You have concepts like these concepts. What are the concepts? Like you have a concept of root, you have a concept of internal node, you have a concept of internal node, you have concept of leaf, you have concept of height, you have concept of height, you have concept of depth, you have concept of sibling, you have concept of siblings. These concepts are not here. All these concepts, they are not applicable here. They are not applicable here. So these concepts like internal node, okay, internal node, height, depth, all these concepts, they are not applicable for tree. So tree, rooted tree is not a tree. Remember this. Rooted tree is not a tree. Rooted tree is not a tree. Is not a tree. Is this clear? Rooted, because in graph theory, I am talking about graph theory. So, okay, like this statement will confuse you. I know many people will get confused because of this statement. Let me tell you that in graph theory, I can say is not a tree in graph theory. But you can think of it as a tree in graph theory. But we think of it as a tree. But we think of it as a tree. As a tree sometimes. We can think of it as a tree sometimes. For example, if I give you this rooted tree, like this is a rooted tree, you can clearly see this is not a tree because tree is undirected connected graph. So you can notice this is a rooted tree. But you can think of this as a tree. What you can do? You can think of this as a tree. Sometimes you can think as a tree. So sometimes what you can do? Sometimes think as a tree. Sometimes thought as a tree. Okay, so this is the difference. Please let me know if you have any doubt. Anyone has any doubt? Tell me. Arpan is asking, rooted tree always top to bottom, can we say? No, Arpan, that is conventional. See, most people, they draw rooted tree from top to bottom. But some people, some applications, that depends on the application. Usually we write root at top. Usually we write or draw root at top. Root at top. Okay, so usually this is what we do. Usually this is what we do. that there is a root, and like this we draw, and like this we draw. But depending on the application, some people can draw like this, depending on the application. Depending on application. Depending on application, some people can draw like this also. Like some people, they draw like this also. They draw like this also, depending on the application. Like this. Some people can draw like this also. But we don't worry about these things. Okay. So don't worry about these things. These things we don't care. So I will remove this slide. But I just want to tell you that usually we write root at top. Okay, because all the applications that we care about, we only write root at top. Any other doubt, anyone? Saurabh is asking, yes, I will upload the notes immediately. Okay. Akash is asking, sir, in depth, we see from node X to root. For height, we see from root to node X. No, Akash. No. No, we don't do that. See, if I ask you like A, like this is what you have. So like A, B, C, D, E, F. If I ask you what is the height of E, to find height of E, what you will do? You will see from E to farthest leaf. Height of E means E to farthest leaf. E to farthest leaf. So height of E will be 1, means E to farthest leaf. And depth of E, and what will be depth of E? That will be root to, that will be root to E. That will be root to E. Okay, so basically, if you want height of E, to watch height of E, you will look down. If you want height of E, you will look down. If you want depth of E, then you will look above. Then you will look above. Is this clear? Is this doubt clear? Height of E, you look below. Okay, depth of E, you look above. So depth of E means root to E, and height of E means E to farthest leaf. Okay. Is this clear now? Anyone has any other doubt? Let me know. Please raise your hand if you have any doubt. Hello, Nikhil. Nikhil.
Sir, am I audible?
Yes.
Good evening, sir.
Yes, good evening.
Sir, I have a doubt in the last question that we have discussed, like suppose U and B are the siblings and they can have a common descendant question.
So for
Very
example,
last question.
you
We
have
have
this A comma B. These are siblings. Siblings means their parent is same. Sibling means their parent is same. But it
yes,
does
sir.
not mean, for example, in real life also, sibling means, okay, let's assume this is a parent. Let's assume this is a parent, and these are the siblings A comma B. Now it can happen that he does not have any child and he has a whole factory of child. It can happen. So that is the idea. So if you have two siblings, then it can happen. So you can notice these are siblings. So their parent is same. Their parent is same. So their ancestry is same. But you can notice that these are the descendants of A. These are the descendants of A. But these are not the descendants of B. B does not have any descendant. Hello, Nikhil? Hello, Nikhil? What is the doubt? Nikhil? Yes, you can unmute yourself.
Sir, I have a doubt. Like let's say U and B are the leaf nodes.
These are the leaf nodes. Okay.
Yes, sir. Sir, so in that case, the descendants will be the like 5.
No, but that question is saying that if U comma, if U is leaf, then V must be leaf. It is not mandatory.
No, sir. I am talking about the second question. They can have a common descendant, and I am considering the case where U and V are the leaf nodes.
No, but they don't have a common descendant. If they don't have, like for example, 1,7, they don't have
Yes,
common
sir.
descendant. There is no common, there is no descendant of 1, there is no descendant of 7.
Okay, sir, I got it now. I considered like if they have like 5 in both the cases, I considered
No,
both the
no, no,
cases.
no, 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 no.
Okay.
That is not the idea. So there is no descendant of one. I can say descendant of one is none. Like they don't have common descendant. See, this word common, this word means at least one. This
Yes, sir.
common means at least one. Yes or no? At least one. There should be some common. But they
Yes, sir.
okay. So siblings, they don't have common descendants.
Okay, sir. Got it. Thank you.
Okay. Any other doubt? Any other doubt, anyone? Hello, Manideep?
Sir, in
Yes.
tree with number of vertices greater than 2, but where it has at least 2 vertices of degree 1. In that proof, I don't understand why total degree is 2 into n minus 1 plus 1.
So this is given. You are given that you have a tree. This tree is given to you. Number of vertices is given to you as, for example, let's assume number of vertices is 5. A1, A2, A3, A4, A5. These are the vertices. For contradiction, we are assuming that we don't have two leaf. The statement is like this, that this is the statement. Prove that at least two leaf you have. Prove that at least two vertices have degree 1. Prove that at least two vertices have degree 1. Okay, at least two vertices have degree 1. This was the proof. This was the idea. You can just check it. Now, for contradiction, I am assuming that you don't have at least two vertices degree with degree 1. What it means? You know that it has degree greater than equal to 1. You know it has degree greater than equal to 1. All of them have degree greater than equal to 1, right? Because it is a tree and tree is connected. So everyone has degree greater than equal to 1, right?
Yes.
Yes, correct?
Yes.
Now, I'm assuming that you don't have at least two vertices of degree 1. What it means, Manideep? I'm assuming you don't have at least two vertices of degree 1. What it means? It means there is at most one vertex of degree 1, right?
Yeah.
It means there is at most one vertex of degree 1. So let's assume this is the vertex of degree 1. It automatically means they don't have degree 1, right? It automatically means they have degree greater than or equal to 2, right?
Okay. Negation of the set.
This is clear?
Yes.
Now, how many vertices are here? N minus 1 vertices we have here. So these total degree will be what? These n minus 1 vertices have degree 2 and this vertex has degree 1. So the total degree will be basically like this. But in a tree, what should be the total degree? This is contradiction. Why this is a contradiction? Why this is a contradiction? Because in a tree, total degree should be this. But the total degree here is more. Like in a tree, total degree should be, this should be the total degree in a tree. But you are getting more. It means this is not a tree. So there is a contradiction. So it means you have at least two vertices of degree 1. Is this clear, Manideep?
Yes.
Any other doubt? Any other doubt? Anyone has any other doubt? Please let me know. Hello, Arpan?
Yes, sir. So I had a small doubt, which is, sir, I did not understand when can a structure be a forest and not a tree? Can I just explain that once again?
This structure, look at this structure. A, B, C, D. Is this tree?
No, it is not a tree.
Because this is not connected. Is this
Yes.
acyclic?
Yes.
Acyclic means forest. Forest means acyclic. Acyclic means forest. This is the definition of forest. Another name for forest is acyclic. Another name for acyclic is forest. Okay. And tree means connected acyclic. Tree means connected acyclic. So this is a forest but not tree. Is it clear now?
Okay. Means like for every tree, it has to be a forest, but for every forest, it cannot be always a tree.
Yes, every tree is a forest, but forest need not be a tree. Every
Yes.
connected forest is a tree. A forest which is connected is a tree. Forest means acyclic. The word is acyclic. These
Exactly.
two words are same.
Exactly. Got it, sir.
Any other doubt?
No, sir. Thank you, sir.
Okay. Any other doubt, anyone? Okay. Thank you. See you tomorrow.